In this particular chapter, we're going to look at two different studies. Both involve the concept of clusters. So let's look at this particular composite triangle group, which has a number of lines of business labeled A, B, C, D, E, F, G, H, I, J. So let's open that. And what we'll do at first is run the related models, or the PTF model, for each line of business, and the sort of optimal PTF model for each line of called goods. So let's highlight them all, and we're going to open them all simultaneously, or run them all simultaneously in MPTF, in the multiple probabilistic trend family modeling framework. And let's now look at the these are the residuals. These are the model displays for each line of business, and you can see some similarities. If you set the correlations to 0, set all correlations to 0, then the models would be estimated independently. There'd be no process correlation. And the model display you would have is the kind of model display you would have for each triangle or each line of business in the probabilistic trend family. Now let's estimate the correlations. Let's estimate the parameters using the estimated process correlation. And you might recall from the previous study where we looked at LOB1 and LOB3, if there is process correlation between, say, two lines of business, then the parameters estimated for one line also use the data in the other line. Let's look at the process correlation. And you'll notice that quite a few correlations are insignificant. You know, things like correlations are not really transitive. So if A's correlate to B and B's correlated to C, doesn't mean that necessarily A's correlate to C significantly. And it could be that A's correlate to B, B's not correlated to C, and A's correlated to C, and so on. So what we try and do now is we try and optimize the correlations in some way. So we go to this particular window where we can actually set up clusters. Now, what is a cluster? Within a cluster, members belonging to the same cluster are in fact significantly correlated, pairwise correlated. But if you take one member in one cluster and another member in another cluster, there's no cross-cluster correlations. So there's a number of ways of setting up clusters. One way you could do it is to retain all significant correlations. Now, if you retain all the significant ones, you might also retain some that are insignificant. So let's try that first. Retain all significant correlations. And you'll see that we have formed 4 clusters. These 3 are in the same cluster. LOB, D and C are in the same cluster. E, G, H are in one cluster, and A, I, J. But you'll see that there's one insignificant correlation that was retained in order to retain all significant correlations. Of course, if you want to remove this one from the particular cluster, in other words, LOB from the particular cluster so it becomes its own cluster, you just double-click on Remove, and therefore, I forget which one that was. Well, it must have been LOBF. If you now add it to selection and you have selected cluster 1, then you bring it back in there. Okay, so it was LOBF. In fact, each one's called LOB. So it was LOBF that in fact was not significantly correlated to B and just to B, and we can remove it so it becomes its own cluster, or we can include it. Another way of sort of creating clusters is remove all insignificant correlations, but when you do that, you might remove some significant ones. So let's remove all these significant correlations. Okay, and let's suppose we decide to go with this set of clusters. There are 5 clusters, and so on. So you can estimate and close, and now you'll see that the cross-cluster correlations are in fact 0. A better description of this is going back into this window, OC, and you can see that all cross-cluster correlations, any two members in a different cluster are in fact not correlated. Now, you have a choice now of actually doing some cross lines of business optimization. Now, you might decide that parameters might be the same in two lines of business only if they belong to the same cluster. If they don't belong to the same cluster, you don't want to set a constraint between two lines of business that in fact are not in the same cluster. So you've got a choice of doing that. If we go to the options, optimization options, let's see that. We go to options, modeling preferences, optimization. And the way I have it set up is you only optimize within clusters only, so that the only cross data sets or cross line of constraints can be set up are only within clusters. Well, let's do that. What you do is typically you reinstate all parameters in each line of business. So in each line of business, we'll re-estimate all parameters, and you just click on O. So now any parameters that have been set to be the same, they would belong, any parameters that have been set to be the same between two lines of business, those two lines of business would belong to the same cluster. So let's check that out. For instance, E, G, and H would belong to the same cluster. Let's check that. So we go back to our, well, we have cluster set up, E, G, and H. And you can see that E, G, and H are the same cluster. And it turns out that that particular parameter that we looked at, this trend parameter from 86 to 94, is significantly not different in those three lines of business. We could save this as the optimal model. Let's call it optimal. Only cross-cluster constraints. Only within cluster, I should say. Only within cluster constraints. It typically wouldn't really make any sense to set two parameters in two lines of business to be significantly non-different, or if they're significantly non-different, to set them the same. But of course, you can override this and do the optimization where you actually have two parameters, say two iotas that are significantly non-different. These two lines of business might not be in the same cluster, but if you like the optimization algorithm, you can set up the options that way that it will set up a constraint. Save. If we do the forecasting now, the forecasts summary will show us what our clusters are. These are our 5 clusters. And if we look at correlations and standard deviations of reserve distributions, this would be this table. For instance, between C and D, the correlation is extremely high. It's about 0.91. Between E and G, we've got a correlation of 0.9. So it doesn't seem like that there's that much diversification between these lines of business. You can get summary graphs for each line, for the aggregate, and for each line. Why don't we do, say, the forecasting now, using this, we've done the forecasting, why don't we do PALD to find out what the predictive aggregate loss distributions are, and we'll do 10,000 simulations of each triangle, and we're actually probably doing millions and millions of simulations because there are many cells per triangle, and this would now represent for the total of all the lines of business what are the quantiles, alternatively percentiles, and what are the value at risk statistics. And you can see that the mean of the reserve distribution is 213 million. The standard deviation is 11 million. This is of the aggregate. It's actually the coefficient of variation is not that high. At the 95th percentile, the value at risk is around 19.6 million. If we just for fun, we estimate the models, but now set the correlations to 0. In other words, we've kind of have sort of complete diversification. If we do the forecast now for the aggregate, if we do the PALD, that's the predictive aggregate loss distributions. Remember, for every cell in each triangle, we're actually forecasting log normal. But now we're trying to find distributions of aggregates of log normals that don't have a nice analytical form. So that's why we do the simulations from these log normals that are correlated, both between within a triangle and between triangles. And now we look at our statistics. The mean, of course, has changed a bit. And if we compare now at the 95th percentile, the value at risk is 18.9 million, whereas here it was just over 19 million. So you need, at the 95th percentile, you need just over, say, $1.6 million additional capital as a result of the lack of diversification. At the 99%, of course, you need more than 2 million additional capital above the mean. Okay, so that tells you a little bit about the lack of diversification in these lines of business. Let's look at 40 lines of business. Where there's about 780 correlations. So if we run just MPTF, for example, and that's the one parameter in each direction. If we look at the correlation matrix, so 780 correlations. If we now try and optimize the correlations, we could go to OC and then say we move all insignificant correlations, and all the clusters have been set up for us automatically. There are 32 clusters in their 40 lines of business, and oops, I forgot to estimate, so let's go back to OC again. We move all insignificant correlations, estimate at close. We could also optimize across. Well, actually, again, we're only optimizing setting parameters across data sets to be the same, only if they belong to the same cluster. Forecast now. If we need to forecast the standard deviation of the aggregate distribution of the 40 lines of business, of the aggregate, then we need to keep track of about 14.8 million correlations between all the cells within a triangle and between triangles. So this is quite computationally intensive, and you can see that it is extremely fast. You have your forecast summary, you have the aggregate, each line of business. We could got summary graphs, and all this could be outputted to any other application in any format you like pretty quickly, because in the next chapter, chapter 5, I think, in the first example, chapter 5, we show you how to create a company-wide report just by using a template, a template that's a standard format that you've already formatted. So it's a standard report format that you'll be using. A template for a standard report format. If you do PALD now, we'll constrain it to 1,000 because we'll be doing over 5 million simulations from all these correlated log normals. And again, you'll see it's pretty fast, and you can find out what the aggregate distribution is. You can create tables, summary tables, reserves by accident year for each line of business, and so on. So you can see actually that so far we've only looked at a number of examples, but MPTF is extremely powerful. If you wanted to now do some adverse development cover on the aggregate 40 lines of business, we go to the RE module, We've got 2 attachment points by default, which are 11.4 million and 11.65 million. So you're looking at around 0.22 million excess of 11.42 by default, because you can change the attachment points. And this is how the profile is going to look for the insurer versus the reinsurer. Notice the reinsurer takes on a very large coefficient of variation. Okay, well, that's the end of those particular 2 studies. Thank you.